Hi, I'm Karthik and I'm going to talk about our work on Flames framework. This work is done with my co-authors from Dartmouth, Amazon AGI, UNC Chapel Hill and UCLA. I've structured this talk into three major sections. First, we will talk about LLM math reasoning and synthetic data and gaps of existing literature. Next, we will talk about our Flames framework. Third, we will describe our results and findings on what matters for math synthetic data generation. LLM math reasoning involves a math word problem where LLM does reasoning and provide a final answer. Math reasoning illustrates LLM's ability to perform structured multi-step logic, which is essential for many real-world applications. There are various data sources people use for improving LLM math reasoning. Uh, Synthetic data offers a cost-effective and scalable approach for enhancing such datasets and generating high-quality training data. Here we list some popular works for math synthetic data generation. Each work proposes a novel synthetic data generation approach and reports improved performance on common benchmarks like GSM-8K and math. However, we argue that these improved numbers is not true reflection of the contribution of these papers. There are multiple factors involved in math synthetic data pipeline, and it is hard to say if the reported gains are due to a newly introduced data generation approach or some other factor like using an improved teacher model. That's one of the limitations of existing research. Also, there are multiple open research questions about the impact of synthesis approach and data quality strategies. Some of these questions include which synthetic data generation approach works best. How does data quality control impact the performance with synthetic data? Under fixed compute budget, should one use the best data strategy or mix multiple strategies? And what are the effect of problem and solution teacher model on final reasoning quality? As part of this work, we will address these limitations and these open questions. Now we are going to talk about our Flames framework. Math synthetic data pipeline consists of multiple steps, usually seed problems, and a teacher model, as you see on the top left hand side, is used to generate synthetic problems based on one or more data agents. Then problems are filtered based on some quality control mechanism. Filtered problems are passed to the solution generation teacher model, which generates multiple solutions. Then solutions are filtered with some quality control mechanism, and final filtered dataset is used for fine-tuning a student LLM. As part of the Flames framework, we list all the factors involved and define fixed values for each of them. For some factors, we perform rigorous study to establish learnings on what works best. Our Flames framework enables controlled analysis where we can vary one factor at a time and see its impact. Now we will move to discussing our studies and learnings. For data quality control, we define various options. We generate multiple solutions for each problem and use consistency of these solutions to control what problems to keep in the final dataset. These options provide various trade-offs of coverage of problems and quality of filtered set. For example, in self-verification, we generate three solutions and we keep a problem only if all the three solutions lead to like a same matching final answer. So this leads to a reduced coverage. We remove some problems, but whatever problems we keep, they have high chances of being correct solutions, so high accuracy. On the other hand, if we look at first approach, we just generate one solution and we keep all the problems. So coverage is gonna be 100%. We are keeping all the problems, but there is risk of generating incorrect solutions as part of this approach. Based on our control study, we established that problem coverage matters more than the precision of solution. as we observe with better performance for first approach as compared to self-consistency approach. Secondly, we notice that majority plus first leads to slight better performance as compared to first. This signifies strength of precision at same coverage. Also, it's important to note that first is a compute efficient approach as only one third solutions are generated as compared to majority or other approaches. So going forward, we will use first as our strategy for all further studies. Next, we develop a taxonomy that clarifies the landscape and functional roles of synthetic data agents. Each of the popular work that we discuss, they consist of one or more of these data agents, but they have not been designed in a very systematic manner to cover all of these key dimensions. Also, we define two novel data agents systematically to address model robustness and model out of domain performance. So, the first one is distraction insertion. We define a data agent which includes redundant information to existing problems, and this agent is designed to improve LLM's robustness. Next, we design another agent which takes math taxonomy topics as inputs and as first step generates subtopics. And then for each subtopic, it generates a corresponding problem. This agent targets out of domain generalization as no seed data is used for generating this dataset. Next, we do fair comparison of all these data agents, and here are some setup details. So I'll move forward. Next, we compare data agents, keeping all other factors consistent, and we discuss our results for this controlled study. We've observed that in-domain complexity agents lead to best gains across multiple metrics. Here I've highlighted, and we can look at their in-domain metrics and robustness metrics and competition metrics, and these are like colored green, which shows higher value as compared to other values. Further, we observe that our two novel agents, they outperform all other baselines on their respective benchmarks. Next, we design a composite mixture of in-domain, out-of-domain, and robustness agents, and this composite data set shows balanced performance across all dimensions. More detail, we call this composition as flame small. More details on how we reach this composition are shown in our paper. Next, we demonstrate that our flames large dataset, which is created by extending flames small and generating more problems and more solutions, and with a final size of 1 million, it outperforms all existing synthetic datasets. Scaling flames to flames XL, which is scale of 1.5 million problems and solution, further boosts average performance to 65.8, demonstrating continued gains with further scaling. I'll move fast on next few slides and just talking about conclusion. First, we observed that gains of flames are consistent even if we use different underlying student model. Our experiments show that solution generation model impacts performance much more than problem generation teacher model, so it is crucial to choose an optimum solution generation teacher model. With that, I'll just summarize what we discussed today. We presented Flames, which is a unified framework which helps compare past and future advancements in synthetic data. We showed rigorous experiments revealing key design principles, what works better for math synthetic data generation. We introduced our Flames dataset and showcased state-of-the-art performance among all public math synthetic datasets. And we argue that our work generalizes to synthetic data for other domains as well, including code synthesis, multiple step reasoning, and planning. Thank you.